Hello everyone. Welcome to Probability and Statistics for Data Science. In a previous video, we defined an averaging operation for random variables, which is called the mean. The mean is extremely useful and is used all over the place, but it has a very important limitation. It can be severely distorted by extreme values, and that's what we're going to see in this video. So we're going to talk about the sensitivity of the mean to extreme values. Remember, let's remind ourselves what the definition of the mean is. We have done a whole video about this where we explain that essentially it's like averaging the random variable. The mean of a discrete random variable is equal to this sum where we weight the values of the random variable. I'm actually plugging my iPencil into my iPad. Okay, I think that should have worked. We basically take every possible value of the discrete random variable and we weight it by the corresponding PMF, the probability that the random variable is equal to that value. And that weighted sum is the mean of the random variable. It represents its average. Very similar for a continuous random variable. In this case, we take an integral of all the possible values weighted by the density. And if we want to approximate these things from data, we just average. And again, I explained this in the video on the mean of random variables. It's not surprising that we average because the mean of a random variable is precisely defined so that we can represent such averages in terms of the random variable. Okay, so essentially this is just a sum of all the data points divided by the number of data points. All right, so now the question is the mean always a typical value? Let's see what we mean by that. So here we have a data set of NBA salaries. Each of these lines in this rock plot represents a player. So here we would probably have this from 2017. So around there you will find LeBron James, for example. And around here you will find most of the players that don't earn as much. And if we look at the mean of the salaries for the whole NBA, for all the players, the mean is equal to $5.86 million. So now we can ask ourselves, how many players earn more than the mean? And what we see is that less than 1/3 of the players earn more than the mean. What is happening, basically the mean is being driven by these enormous salaries of a small number of players. So in that sense, one could argue that maybe it's not that typical. We could not really say that the typical salary of an NBA player is 5.86 million. There's only 1/3 of them that earn that much or more. So in order to delve a bit deeper into what is going on, let's take a look at a cartoon example. We're going to consider a random variable that has constant density between minus 4.5 and 4.5. So this was what you're seeing here. And also it can have some extreme values with small probability. So its density is also constant around a value x, which is potentially very large. And the density is constant between x minus 0.5 and x plus 0.5. So if you think about the samples, sampling many times from this random variable, essentially what you're going to see is mostly samples here, but from time to time, you're going to see a sample there. All right, so now we're going to derive the mean of this random variable. We apply our formula. The mean is the integral of all the possible values of the random variable, weighted by the probability density. The probability density is only non-zero between minus 4.5 and 4.5. and x minus 4.5 and x minus 0.5 and x plus 0.5. Remember that x here is just a parameter, it's just some value that is very large. So now, what is the value of the density? The density has to integrate to 1. Since it's constant in an interval of length 9 and length 1, the total length is equal to 10, the density is equal to 1/10. So now we have to integrate 8 times 1/10, this is where this 1/10 comes from minus 4.5 to 4.5. The antiderivative of a, let me erase this so that it's clear. The antiderivative of a is a squared divided by 2. That's where this 2 is coming from. All right, and here, basically we evaluate a squared at 4.5 and then minus 4.5. So we have this first term that is going to cancel out. It's going to be equal to 0. And then we have this second term, where we evaluate a squared divided by 2 at x plus 0.5 and x minus 0.5. This guy is going to go to 0. This guy now we're going to expand it. And when we expand it, we see that we have these cancellations. This x squared will cancel with this guy. This 0.5 will cancel. And we get 2x divided by 2, which is just equal to x. So the mean of this random variable is x divided by 10. If we take x to equal 1 million, then the mean will be 100,000. If we take x to be 1 billion, then the mean will be 1 billion divided by 10. You see that the mean of the random variable, which is here, is completely dominated by the 10% of most extreme values. If we take them towards infinity, the mean goes towards infinity with them. So the mean is completely distorted by these extreme values. So how else, what could we do to characterize a typical value in such scenarios? Well, we can go back to our question that we had when we talked about NBA salaries, which is how many players earn more than this value. And for a typical value, we would expect about half of them to earn more. I have essentially just defined the median, not the mean, certainly not the mean, the median of a random variable, which we already discussed a while back. Okay, so remember that the median Q of a random variable A satisfies that the probability that the random variable is smaller than the median or larger than the median is equal to 1/2, or equivalently, the CDF at the median is equal to 1/2. So let's compute the median for our example. We have to integrate, so we have to compute the probability that the random variable is smaller than Q, and then essentially set this equal to 1/2. That's going to be our strategy. So just by looking at what the density looks like, it seems that the median is going to be between minus 4.5 and 4.5. We will have to check afterwards. If that is the case, then that probability is just obtained by integrating from minus 4.5 to Q. And what do we integrate? The density, which is equal to 1/10. So this is very easy. This is just Q minus 4.5. So it's Q plus 4.5 divided by 10. When we set this equal to 1/2, then basically Q is going to be equal to, this is going to go up here. So it's going to be 5 minus 4.5 is equal to 0.5. We see that indeed it's in here. So this formula for the probability is correct. The median of this random variable is 0.5. At 0.5, we have half of the probability to the left, half of the probability to the right. Notice that there's absolutely no dependence on x. If we take x to be equal 1 billion, it doesn't matter. Half of the probability stays to the left of 0.5, so the median is at 0.5. In that sense, the median is a much better definition for the typical value of this random variable because of the presence of these extreme values than the mean. The mean is completely distorted. This red line, as we take, so here we're plotting this for x equals to 100. If we take x to several million, then the mean would go with it. The median would stay there because half of the probability will stay here. And as long as that happens, then the median will stay at 0.5. In practice, we don't compute the median, we compute the sample median, which is the point at which the empirical probability that the data is smaller than that point is 1/2 or greater than that point is 1/2. This can be easily computed by just ordering the data points and picking the middle one. And if you have an even number, then basically you pick the midpoint between the two middle ones. If we do this for our data set of NBA salaries, we obtain that the median NBA salary is 2.39 million. And by definition, half of the players earn less, half of the players earn more. That's a much more reasonable way to describe a typical NBA salary than the mean, which is almost double, 5.86 million. Actually, way more than double. I don't even know how to multiply anymore. So what have we learned? We have learned that the mean can be severely distorted by extreme values, and that in such cases, we should use the median instead to represent the typical value of an uncertain quantity. Thank you very much.